Algebra 2, we are in Chapter 4, Section 4. It is titled, Evaluate Logarithms and Graph Logarithms. So let's warm up first. Let's find the inverse of this function. We did this last chapter. If you remember, we switch out the x and the y and solve for y. So I'm going to add 5 to both sides. I get x plus 5 equals 3y, and then divide everything by 3. So y equals x plus 5 over 3. There you go. All right, an account that pays 3% annual interest compounded continuously has a balance of $10,000 on June 1st, 2008. If no money is added, what's the balance on June 1st, 2010? So I think that would be our A equals PE to the RT. Our initial amount would be $10,000. E, the rate is 0.03, and then the time, we're going from 2008 to 2010, so that is 2 years. Handy dandy calculator. 10,000 times E to the 0.03 times 2. That would be $10,618 and 36 cents, actually 37 cents. Cool. All right, into the lesson. All right, today we're doing logarithms, which logarithms are our way to solve things when they're in the exponential spot. Example, and then I'll talk about it a little more. Right here, if we had anything raised to the x power and I'm trying to solve for x, we need logarithms. So back up to the beginning. We know that 2 to the second power equals 4 and 2 to the third power equals 8. However, for what value of x does 2 to the x equal 6? This one isn't as easy because it's not one of our integers like 2 and 3. Mathematicians define this x value using a logarithm and write x equals log to the base 2 of 6. That's what this says. X equals log to the base 2 of 6. The definition of a logarithm can be generalized as follows. So this would be a logarithm with base b. Let b and y be positive numbers with b not equal to 1. The logarithm of y with base b is denoted by log base b y and is defined as follows. Log base b y equals x. If and only if b to the x equals y. That right there is our clue. Okay, I've got this and it relates to this. Okay, we can go back and forth. Okay. Log to the base b of y equals x. B to the x equals y. I could do it with anything. Log the base 3 of 4 equals x. That means that 3 to the x equals 4. Okay, it's just putting everything in different orders. Okay? Let's try a few. Okay, we're just writing things in exponential form. If you see this is on the base, it becomes, I don't know, the normal, the ground level number. If this is in the basement, it becomes the one on ground level. Okay, this is the equal sign, it becomes the exponent. And this just moves spots. So for letter B, we have 4 to the 0 equals 1. C, 12 to the 1 equals 12. D, 1/4 to the negative 1 equals 4. Okay, it's just a pattern that you have to learn and get used to. If you look at parts B and C of example 1, they illustrate 2 special logarithm values that you should learn to recognize. Let b be a positive real number such that b is not equal to 1. Right here, the logarithm of 1. The logarithm base b of 1 equals 0 because anything to the 0 power equals 1, anything at all. And then the logarithm of b with base b. Log base b of b equals 1 because anything raised to the first power equals anything, equals the same thing. Okay, so when these two match, my answer holds. Excuse me. Let's try a few more. Okay, remember this becomes ground level. 3 to the 4th power equals 81, ground level. 7 to the 1st power equals 7, ground level. 14 to the 0 power equals 1, and ground level. 1/2 to the negative 5 equals 32. All right, moving on. Here for evaluating the logarithm, we're actually, we ask ourselves questions. Okay, every time I teach this, I just call it the what if, or to the what power, to the what power. Okay, so evaluate just means solve every time in math language. So this right here is ground level. 4 to the what power equals 64. Okay, the what power equals 3. Or 5 to the what power equals 0.2. Well, 0.2 is 2/10, which is 1/5. So my what power has to be a -1 to put that 5 in the denominator spot. Okay, more what powers. 1/5 to the what power equals 125. Well, I need that 5 to move to the numerator, so it has to be a negative. And then 5 to the 3rd power? Yep, to the 3rd power is 125. So 5 to the 3rd power equals 125, but I have to move this to the numerator, so that has to be a negative. So my what power equals -3. And then 36 to the what power equals 6. Well, that looks like a square root, and that means our what power has to be 1/2 because that's our symbol for square root. All right, special logarithms. A common logarithm is a logarithm with base 10. That's important. It is denoted by log 10, or simply just log. Whenever I just write log of anything, I don't have to write the 10. Okay, just like way back when, if I would write just a root, I don't have to write, I don't have to write the 2. I know that when it's a root, we assume it's a square root. A natural logarithm is a logarithm with base e. We just learned e in the last section. It can be denoted by log base e, but it's more often denoted by ln. So log base e is the same as ln, and that is a button on your calculator. Log base 10 is just log, and that is also a button on your calculator. So we can do this with our calculator. If you want to take the log of 8, note it is base 10, but we don't have to write that. We can use our calculator and get out our display. And then we can check it, which is pretty cool. Just do 10 raised to this number, and it should come back to the beginning. And then the natural log of 0.3, we've got that button, okay? Which gives us this, and we can check it by doing e raised to the answer and making sure we get to the original problem. Moving on to example 4, tornadoes. The wind speed s in miles per hour near the center of a tornado can be modeled by s equals 93 log d plus 65, where d is the distance in miles the tornado travels. In 1925, a tornado traveled 220 miles through 3 states. Estimate the wind speed near the tornado's center. So we know that d equals 220. Yep. S equals 93 log of 220 plus 65. Okay, I'm going to actually move that to a new page. S equals 93 log of 220 plus 65. Now I can actually take the log of 220, log 220. I get 2.34 and some change. I'm going to multiply that times 93, and then add that to 65. S equals 282.85 miles per hour. Not too bad. All right, evaluate the logarithm. Use the calculator if necessary. Here's the what if. So 2 to the what power equals 32. I don't remember. It's not 4. There it is. It's 5. So what power equals 5? 27 to the what power equals 3. Well, I think that is a cubed root. So my what power would be 1/3, but I'm going to go ahead and check it. Yep. 1/3. Okay, here I have base 10, so I can just plug it into my calculator. Log 12 is 1.08. And then natural log, so ln 0.75 is -29. And use the function in example 4 to estimate the wind speed near a tornado center if the path is 150 miles long. So 93 log 150 plus 65. So log 150 times 93 plus 65, and I get 267.38 miles per hour. Okay, inverse functions. This is when you guys would have grown. No, Miss Carly. If we look here, by definition of a logarithm, it follows that the logarithmic function g of x equals log base b of x is the inverse of the exponential function f of x equals b to the x. This means that if we test the inverse functions, and we learned this last chapter, not everybody fully understood it, but if we test the inverse functions, we should get x. So g evaluated at f of x means that this is g, log base b, and instead of x, so this is log base b of x, but instead of x we put b to the x. And remember, we just talked about when these two match, this is my answer. So this would be equal to x. And f, let's do this one in blue, f evaluated at g. So f is b to the x, but instead of x, we write log base b of x. Well, when we take b raised to the log base b, my answer is x. Okay, this is something you have to learn. You have to know it, okay? And this is me telling it to you. When you have log base b, b raised to something, when these match, my answer is x. When you're doing b raised to log base b, that's my answer, okay? Let's try it. Simplify the expression. So I have 10 log base 10 of 4. Okay, all of that matches, so my answer is 4. And here I have log base 5. It's not really 25, it can be 5 squared, right? So we have our answer. When all of this matches, that's my answer. Pretty cool, huh? All right, find the inverse of the function. I'm going to remind you, early on in this lesson we learned a few things. Log base b of y equals x goes back to b to the x equals y. All right, so to find the inverse, let's go ahead and switch this. X equals 6 to the y, and then I'm going up here and using these. So I can say log base 6 of x equals y. So first we switch our variables, then we go back into logarithmic form from exponential form, right? Same thing here. Let's switch our variables. X equals natural log y plus 3. Going back up here to this form, remember this is base e. I can say e to the x equals y plus 3. Subtract 3 from both sides. Y equals e to the x minus 3. That one was a tad bit tricky, wasn't it? All right, let's simplify the expression. Remember, when all these match, my answer is x. Those are lovely, aren't they? Log base 7 of 7, my answer is this. So you just have to remember the pattern and you'll be good. Simplify the expression, log base 2, 64 to the x. 64 is also 2 to the 5th. So log base 2 of 2 to the 5x. When all of that matches, my answer is 5x. And then e, that's base e of 20. All of this matches, so that's my answer. I just caught a mistake. This should be 6. So the answer is 6x. Sorry, 2 to the 6th power, 64. All right, now we are finding inverses. And remember, with inverses, let's switch the variables. X equals 4 to the y. And I'm going from logarithmic to exponent. No, I'm going from exponential to logarithmic. So I'm just going to write down my form. And this is just the order. I know it's not the variables that we're using, but... So that second part is the one I have. So the 4 becomes my base. Log base 4 of x equals y. Perfect. Okay, for some reason I have an easier time with these. So I'm doing switch the variables. Nope. I caught it. I know you guys love catching my mistakes, and I love that you love catching my mistakes. So I'm going to do e to the x equals y minus 5, and then add 5 to both sides. So y equals e to the x plus 5. Graphing, I know. Graphing logarithmic functions. You can use the inverse relationship between exponential and logarithmic functions to graph logarithmic functions. So we know the graph of f of x equals log to the base b of x is shown below for b is greater than 1. It is right here, that one, and for b is between 0 and 1, and that is this one, okay? Because f of x equals log base b of x and g of x equals b to the x are inverse functions, the graph of them is a reflection over the line y equals x. That line right there, that's the line y equals x. The y-intercept is 0, the slope is 1, right? Okay, right here too. The y-intercept is 0 and the slope is 1. So it's a reflection, which means this red line reflects over, this red curve reflects over this dotted line and becomes the blue curve. Okay, the red curve reflects over the dotted line and becomes the blue curve. Note that the y-axis is a vertical asymptote of the graph f of x equals log base b of x. The domain is x is greater than 0, and the range is all real numbers, which is backwards from what we did in the last few sections, right? I know graphing is hard. I get it. Let's try, though. So here, let's just plot several points, make them somewhat convenient. If I plot 0, nope, 1, if x is 1, that just means 3 to the y equals 1, and that's going to match with 0. Okay, anything to the 0 power is 1. And then I can plug in 3, x is 3. So that would be 3 to the y equals 3, so y is 1. So 3 comma 1. And then 3 to the y equals, I don't know, 9. So I can do 9 comma 2. If I plug those in, I can get a pretty decent graph. So 0, 1, no, 1, 0, 3 comma 1, and 9 comma 2. We know that it's not going to cross the y-axis because our domain is x is greater than 0, and our range is all real numbers. Okay, let's plot a few numbers again. That 1 comma 0 is always going to be one of my points because 1/2 to the y equals 1. Anything raised to the 0 power is 1. Let's plug in 4, so 1/2 to the y equals 4. I need it to be a negative number to get my 2 in the numerator spot, and then square it to become 4, so negative 2. And then 1/2 to the y equals, we did 8. I know if I cube a 2, I get 8, but it needs to be a negative 2, a negative 3, I'm sorry. So 8 comma negative 3. That's not easy. I know you guys can do it, but plot your points. I didn't even do 2 comma negative 1. I don't know why I'm plotting a point there. I did these 3. Okay, my domain, x is greater than 0. My range is all real numbers. And then it gets harder. Blah. Translations. You can graph a logarithmic function of the form y equals log base b of x minus h plus k by translating the graph of the parent function. Remember, h is left right and k is up down. So here I have h is negative 3 and k is plus 1. So we're going to go left 3 and up 1. But we're going to graph log base 2 of x first. So my points are going to be 0 comma 1. That would be 2 to the y equals 0, or y equals, I'm sorry, 1, y equals 0. And then 2 to the y equals 4. So x is 4, y is 2. And then I'll do 2 to the y equals 8, where x is 8, y is 3. So if I graph those 3 points, and I'm going to graph them in blue highlighter, I have 1 comma 0. I did those backwards. I'm so sorry. When I plug them in backwards, it's hard for my mind to really wrap my head around it. So this would be 1 comma 0. And these are all backwards. I bet you guys were just rolling with laughter. X, Y. Sorry. So we got this. Okay, 2 comma 1, which we didn't even do. That's all right. 4 comma 2. And I did 8 comma 3. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Right there. So once I plot those 3 points, I'm going to go ahead and move left 3 and up 1. Left 3 and up 1. And if you see me do my homework, it's exactly what I do. I plot the original points. I may not draw the curve, but I plot the original points, then I move them and plot the new one. Okay, practice a few. Log base 5. I'm going to do this right here is 5 to the y equals x. So if y is 0, x is 1. If x is 25, y is 2. And then 125 comma 3, right? But I know I can plot 1, 0. Then 25, 2 is way over there. So we don't have a graph big enough to plot that one. Domain is x is greater than 0. Range is all real numbers. Okay, a little bit harder. H is 3, so we're going to go right 3. K is 0, so we're good with that. But I need my form, so we're graphing the parent function, log to the base 1/3 of x. So y to the 1/3 equals x. That's not right. Sorry about that. Base b, so it's 1/3 raised to the y equals x. So when y is 0, x is 1. When y is -1, x is 3. That's pretty easy. And then let's do xy. When y is -2, it's going to flip that to the numerator and square it. 9. And then we want to move it right 3. So let's graph it first. 0, 1. Haha, 1, 0. Oh my goodness. Over 1 up 0. Over 3 down 1. 1, 2, 3 down 1. And then I don't think I can do the 9. 1, 2, 3, 4, 5, 6, 7. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9. Down 2. 1, 2. So now we're going to move it. Right 3. 1, 2, 3. 1, 2, 3. We have our new graph. So here my domain is going to be x is greater than 3, and my range is all real numbers. Okay, parent function, y equals log to the base 4 of x. We're going to go left 1 and down 2. So my parent function is there. That means I have 4 to the y equals x. When y is 0, x is 1. When y is 2, x is 16. Whew. How about when y is 1/2? I'm going to take the square root of it, and x will be 2. I'm running out of space. Go ahead and graph them, 0 or 1, 0. And we'll do 2 and 1/2. 1, 2 and 1/2. I'm going to go change colors. Left 1 down 2. Left 1 down 2. Perfect. Left 1 down. Oh. I went the wrong way. Haha. That black dot is not correct. Over 2 up 1/2. Over 2 up 1/2. Thank goodness. Now let's go back to green. Left 1 down 1, 2. Woohoo! My new curve. Where my domain x is greater than -1, and my range is all real numbers. We made it. Daily homework quiz. Okay, push pause, try these. Okay, it's good practice. And the last one. Good work today. Proud of y'all.